exceptional speaker who's quite brilliant and has been really at the forefront of tech. He's got more than 15 years of experience in technology. Founded the very first Linux user group in Buenos Aires, Argentina. That was way back in 1994. And quite interestingly, before he got into tech, he was a neurosurgeon. And was bored. And was bored with it and ended up at tech, yes, like he said. That was his words, mind you. So please welcome the VP of Infrastructure or the VP of, we have two hats there, Product and Infrastructure at HPCC Systems, LexisNexis, Dr. Flavio Villanustre.
I hope everyone can hear me now. Can you hear me now? Good. Okay. Thank you very much for coming. We have a great crowd, and I see that people are already invigorated with the little giveaways and all this stuff. So I won't make this too long, but I'll try to go over as much as I.
I don't know, you gotta get closer or it's battery.
Can you hear me now? Is this good enough? Yeah. Well, that's good. So, hello? That's better? Hello? Thank you. So, I try to go over as much as I can different, at least first the basic functionality and what it is and the basic architecture. But I need to know a little bit more about you. How many of you have some programming experience in any language, any computer language? Very good. Okay, that's good. Okay, then we'll go faster. That's it. Okay, so let's get started. I'll do a little bit of history initially, and then we'll get into the real meat. About 12 years ago, or maybe 13 years ago now, we got into big data. Essentially, big data by those standards, not as big as today, definitely. But big enough that the standard technologies wouldn't be able to cope with the type of needs we had. We had the need for some very heavy analytics on the data. We were trying to link data across a lot of different data sets. And in many of these cases, linking wasn't just a clear key-based linking. In many cases, it was fuzzy matching, transient linking across intermediate steps. And it required to do this efficiently to use some heavy clustering type of techniques. We were using conventional technologies by then. We were using Informatica, Initio, relational databases, Oracle Sybase, well, you name it. This is back late 90s. But those technologies weren't cutting it. It was really hard for us to get the job done, and even if we could get it done, it would take so long that it was almost unfeasible for the business. So we decided to tackle the problem in a different way. Based on the majority of the data problems and the way they are normally formulated, you can tackle this using what is called a parallel approach. Essentially, well, if I need to apply a transformation on a given data record, and I have 1 million data records, can I split that across a cluster of machines and apply transformations in parallel? Yeah, why not? I just need some sort of data workflow system across them and some platform that allows me to do this in a coordinated way. So, seemed like a good idea. We started exploring this, and we came up with a platform that would allow us to do these data transformations and data integration processes in parallel using commodity machines. So no more the big E10,000 Sun servers or E6500s or whatever we had at the time. And now we could use just standard PCs. No more than that. And once we did this, obviously we got a few different challenges along the way, making this very short. One of those was, well, we want to make this a general platform. We don't want to have to do low-level coding every time we want to introduce a new process in the data. And no, there was no Pentaho again. So how do we do this in a way that is efficient, that we can have a very succinct programming environment that allows data analysts to be very efficient, but at the same time being able to do a lot of complex processing. So look at the languages at the time and look at different areas, and we could go with a procedural type of language, like imperative programming, C or C++ or Java. Could have done some of that, but it's still very low level. Getting to program data workflows in these languages gets quite hard. We could have used SQL. As a matter of fact, it started like SQL. We said, well, maybe we can create an SQL interpreter of sorts, or optimizer compiler of sorts, and do this. That might got us halfway through, and we used SQL in the beginning, and you can still see some of the, if you go to our GitHub repository, our portal, and check some of the files are called HQL, and HQL stood for this version of SQL that we have. That was going to change over time. But SQL has a couple of different problems. One is that it's not very friendly with long programming environments. So if you have a lot of programmers, if you have collaboration across them, if you have complex programs, SQL quickly becomes unwieldy. You start getting into a long string of within a query with a ton of subqueries and filters and other conditions. And when it comes to trying to understand what you were trying to do 6 months ago or someone else, which is worse, it's almost impossible. And we wanted to have also code reuse and the ability to provide for encapsulation. Not only code encapsulation, but also code and data encapsulation. So SQL got us halfway. We looked at some of the other languages, functional programming at that time, and other declarative models, and we decided to come up with our own language. And we wrote, that's how we wrote original VCL. David Davis, who was the answer to the question, and a team of developers, the ones that developed the platform, came originally from Borland. We acquired the business unit that used to develop Clarion, for those that might remember the mid-90s, the next generation language, 4th year or whatever it was at that time. And before they were the ones building the Borland compilers, Turbo C, Turbo Pascal. How many in the audience remember those languages? Well, these guys came on board, and they are still with us. Many years later, one of them passed away last year, unfortunately, but the others are still with us, and they are still driving the core development of the platform. So ECL was born as a language to do complex data processing in a way that it can be managed efficiently in modules that can be reused as extensible language that can grow from, essentially allow you to grow your language from the bottom up by adding new functionality and code your applications top down as you normally code them. So we built, at that time, this component, which is Thor. Essentially, what we used to call data refinery. It's a back-end type of ETL and data integration system, and it's programmable in ECL. ECL is here, and allows you to do all these operations in data, which could be as simple as a simple transform or mapping or remapping of the data. It could be as complex as a machine learning algorithm or a clustering or a statistical analysis or any other functions around the data integration cycle. But we were using at that time conventional relational databases to do the data delivery. And that got us halfway there again, and it wasn't as effective as we needed, and it didn't scale. Once we got to the larger server again, when we had more customers, now we need to start sharding the databases and spreading them across the system. Coordination became difficult. Availability and reliability became also critical. And I don't think Eric mentioned it, but LexisNexis, well, he mentioned that we have data services. And this data service in particular was a critical data service that requires 99999 availability, and these traditional database systems didn't get it. So we decided to build another parallel system called Roxie, which provides for distributed data delivery. Essentially a sort of programmable database using this common ECL layer that allows to do data delivery, but also do complex data queries, real-time analytics on your data. Let's say, try to now take a high-level view of this. Think if you are, for example, let's put an example now that it can be kind of complex. Let's say that you have some historical data, and you build a classifier, and you classify this data in some way. You use this historical data to train your classifier, right? So, well, I have this data about my customers. I train a classifier. I do that on Thor. I build a model with this classifier. Now, I can deploy my model on Roxie. And now I can have real-time queries coming from my customer activity as they are performing the activity. And I can use the model that I built to determine how I need to classify those records in real time. This is a quite common application for us. I might have data that I need to deliver using complex queries, relationships between the different data elements. I may need to do, for example, fuzzy matching, full text searches, Boolean, some semantic type of analysis on the data. And if I need to do it in real time, well, I guess you could move some of the functionality to the application and use traditional database, but it quickly becomes complex. So having these analytics the closer possible to your data makes them faster, makes them easier, and it encapsulates the data together with the analytics. It makes for a more consistent type of data. Let's move to the next one. Three main components. Thor, I said this before, Thor and Roxie both are using commodity nodes. They have no shared storage, so storage is local in the nodes. Data is loaded in these nodes, and processing is leveraged across the entire environment. Of course, you come now and say, well, what happens? You talked about all these linear transformations of the data that are in nature embarrassingly parallel. That might be okay, but what happens when you have some operations, which are quite common, will require some knowledge about what the other nodes have? Imagine, for example, a sort, a simple sort. You need to sort the data set now, and you have the data set across 100 nodes, or 50 or 1,000. Well, you need to know how to distribute the data. And I don't want to get into too much detail there, but yeah, you could use, for example, a radix sort, which essentially uses the first pieces of the key to define which node you take. But what happens when your key space is not complete, or is skewed, heavily skewed? You'll have some nodes that will get a ton of data, some nodes that will get a little data. We built our own sort algorithm, which we have a few patents on, and hopefully to be released in open source as well, so it's all there. Essentially, the sort algorithm that we built builds a histogram, distribution histogram of the key space, and now determines at the beginning of the process which nodes get which pieces of the key space in order to have a balanced distribution of the data across the entire cluster, which is quite cool. If you ever try to use radix sort on Hadoop or any other environment, you will end up with these heavy skews that are always a headache. And avoiding the skews is very cool. In the HPCC systems, when you do a sort or a distribute operation, and you use, well, the system tends to do a lot of heavy lifting for you in the back end. So if you just say sort, well, it will pick the right sort algorithm. We have several there. And one of those is this algorithm that computes this histogram and defines your data distribution based on the key space and ensures that there are no skews across the system. And you will see, we have some graphical execution plans, and I'll show you a little bit of that. And you will see that you may start with some data that is heavily skewed across the cluster, after you run some of these data operations, the data gets unskewed. It gets distributed evenly across the nodes because of this algorithm. We put a ton of optimizations over the years. There is one important thing there. This here is the declarative language. You tell the system what needs to be done rather than how to do it. And I know I like computer languages, so I learned a little bit of all of them. But I used to be a heavily imperative type of programmer. So coming out of this control freakness addiction that I used to have, it's hard. Trying to let the system do more for you instead of trying to mandate, well, no, go and iterate every record, and now look for this piece of the record, and now go 3 characters to the right, and then do this. It's a little bit a different model. But it really works. Yeah, sure.
The person data build process, what does that mean? Is that the histogram? What does that mean, person?
Oh, yeah, sure. Well, this one in particular, well, this talks specifically about a process that we do. One of the databases that we have has data about people. And it's a large database. At the peak of the process, it has about 30 or 40 billion records per process. This is a classic clustering type of problem. We are trying to build relationships between different records. And we don't have a key. In many cases, we have transposed data. In many cases, we have typos. And we need to continue, keep calculating. For example, I don't know how many of you are familiar with text processing a little bit. There is a thing that is called edit distance, or Levenstein's distance, where you calculate the distance between 2 different words based on the number of letters that are transposed, or that are substituted, or that are inserted or removed in the word. Well, in many of these cases, we use edit distance to calculate how different those 2 pieces of data are, and based on this closeness or not, we define what the weight for that link is. But we also use frequencies of these words. As a matter of fact, we use the inverse of the frequency, which is specificity. The more specific the word is, the higher confidence I have that that word might help me link to another record. Let me give an example, simple. Imagine that I have a record that says 2 records, and both have different fields, but one has, each one of them have these 3 fields. First name, last name, and city. And let's say that the first name in both records is John, the last name is Smith, and the city is New York. How good, how confident can I be that these 2 records are linked to the exact same person? What do you think? Not much. How many John Smith in New York City are there? A lot. How about if I told you that the first name is Flavio and the last name is Villanustre in New York City? How confident could I be? Probably 100% confident. Well, maybe not 100% because this is statistics, but let's say after I do my Laplacian smoothing, it might get to 99.9999%. Well, specificity is important to determine this, and this is part of the cluster algorithm as well. This helps identify the clusters, and based on these clusters, we know which records are part of the same identity. And it goes even one step beyond that. What if I don't have 2 records that match exactly in any field, but I have a 3rd and even a 4th record that match or share some of these fields? Maybe I can now build a transitive relationship across these other records to find the connection between the first 2 records. It gets quite interesting, and we've been doing this for many, many years. And I could take hours about it. But it's a cool problem, but it's very complex. When you need to do this, many of these algorithms are recursive, heavily recursive. Think of it when you just run a simple k-means. I don't know how many of you are familiar with clustering techniques. K-means clustering. Essentially, you have a lot of points in some hyperspace, and then you try to, and you have some centroids, some potential points that could identify clusters. And now you run a round of this algorithm, and it will try to move the centroids to put them close to all the points. Then it reassociates the centroids and then runs again. And then it does it again, over and over, until it converges. Hopefully to a global minimum, but it could be a local minimum too. So you may need to run it several times. And this takes a lot of computing power. It's something that you really want to do close to the data. As close to the data as you can. If you need to move your data around to do this, well, and it's big data, it will take forever. Our Roxie engine, same thing, distributed, local data on the nodes, but there are key differences there. Roxie is built for real-time delivery. Essentially, the queries in Roxie run in parallel. You load queries, and essentially you build these data transformation queries on ECL, or you run them, you build indices or whatever you need to build on Thor, do all the cleansing, hygiening, linking, whatever you need to do. And then you move this data, the pre-fabricated data, this index data, to Roxie. And you deploy some of these queries, what we call query packages to Roxie. Essentially exposing a web service interface in the front end, so RESTful, JSON, whatever, JVC, whatever you want to use there. And you have there, think of these Roxie queries as equivalent to PLSQL. I don't know how many of you are familiar with the store procedures in databases. Probably a lot of you, right? Well, think of them as store procedures. You have some way to process data, you load your database with this way of processing the data, it's algorithms, and they expose a parameterized interface to the world. Again, web services, JVC, whatever it is. All these queries are available at any given time, and they will run in just milliseconds. So you will just send a request, essentially connected to the web interface, or sending a JVC request, and you will get the answer in just a few milliseconds, right? So far so good. Now, Roxie also builds high availability. Remember my original premise when I said, well, we need very high availability for these services. Our customers are one click away from going somewhere else. So every component in Roxie is redundant, and there is no single point of failure. There is no coordination service. Essentially, Roxie won't get much of the details, but if you look at this diagram, every node in Roxie has two components loaded. One component is what we call the Roxie farm, and the other component is what we call the Roxie worker. And when you have a load balancer in front of them, right? When you run a query in Roxie, the load balancer will assign any farmer, essentially any node. Farmers will have a way to know which workers have the right pieces of data to fulfill that query. We use a hierarchical key structure. You have also patents on those. Those are also open source, so you can take a look. This is the cool thing about open source, and use it. The cool thing about this is that we use UDP multicast for the, I don't know how many of you are familiar with networking protocols, but UDP multicast, and we have channels. So essentially every worker that has a particular piece of data subscribes to a channel and listens to a channel. Whenever a farmer has a request for that channel, sends a request. There may be two slaves, maybe more than two. Maybe you will have, they need to have high availability. You have 5 or 6 or 7 workers listening to that. And whoever is listening, well, they have a protocol to define who is the one that will take that request. And it tends to balance itself. We have a couple of techniques there. We have some kind of predictive type of response. But in any case, the interesting thing is that, and this is cool about Roxie, is that if you need more availability, you can add more of these workers, essentially more copies of your data across the system. But also, every time you add a new copy of data on the system, you're adding performance. Not speed for individual query, but more queries in parallel, concurrency. A normal Roxie in our environment usually deals with about 5,000 to 10,000 queries per second. And this is just a normal size. I think they have like 100 nodes, so it's not that much. Well, in our size of things, it's not that much for the size of the data. ECL, I said before, very succinct. I'll show you a couple examples of ECL. Very, well, I won't say very easy to program. Well, it has a learning curve as any computer language, but if you come from the SQL world, it is not that hard. It has the same type of operations, filtering, it has a data transformation, data integration type of function functions as well. And many of these operations are just one function, one type of, or one word, essentially, in some parameter. So it makes it relatively easy to learn, and it allows for code and data encapsulation. If you have data sets, and we have, how many of them? We have probably 10, 20,000 data sets that we receive on a regular basis. Some of them get updated even more frequently than daily. Some of them get updated weekly, some monthly. And when you have a ton of them, and you have some people that take care of these data sets, essentially the ones that receive the data sets and verify that the data is complete, that it's not broken, that the layout of the data has been changed and all that, they can build DCL as a wrapper for those data sets. So imagine that I have a data set that I'm the one that is custodian for this data set. So I build my DCL wrapper and expose a standard interface for that data set. If the data set changes, and it happens, believe me, it happens every time, particularly if you're not in control of those data sets. Let's imagine that those come from the outside, from other providers. Well, you can still maintain your interface consistent so that my main ECL programs will be able to deal with any layout or format of the data set, while I just take care of changing the wrapper as is needed to take care of all the things. I have some horror stories, so I'm not getting into that. But yeah, data sets can change at any given time. No alerts. And I think this is the most important thing. You don't need any other moving parts. Having a single platform that has the data, the backend data transformation and integration engine, that has the data delivery engine, that has a single consistent language across it, and it has all the production-ready components, all the monitoring, management, consistent workflow service, data integration services, connectors, everything part of the same platform. You don't need to look for 15 different vendors and try to come up with different businesses, which is what happens a little bit with Hadoop. Sometimes companies that went to Hadoop early came back because, or they are kind of disappointed because of the need to integrate a ton of different technologies. Well, you can go and take Hadoop. And I've been involved, at least looking at Hadoop since back in 06 and 07, whenever I learned about it. And yeah, you could download Hadoop, that's fine, and that'll leave you there for general use. But, oh no, wait, I need something higher level. Oh, I need to get big. Oh, let me download the pig, please. Oh, but wait, this pig doesn't run on this version of Hadoop. Let me go and take off, throw away my Hadoop, get the other version for pig. That's good. Now with the cloud data distribution for Hadoop, kind of works better. But, well, but then, now I want to make it, I want to know what's going on. Oh, you need to read the logs. Well, no, you can get Karmasphere. By Karmasphere, that gives you the nice graphs on the logs. Well, that's cool. Okay, get Karmasphere. Well, I need to do data delivery. What am I going to use? I could use a key value store, like HBase. But then I need to go and download HBase and make sure it runs on the version of Hadoop. Oh, maybe Cassandra, but that's key value too. So if I need to do complex querying, I need to now put all these analytics on my application. So it gets very, very complex. Having a one thing where you can rely on end-to-end on the solution, and you just need to build your front-end presentation layer to the world, it's much easier. Oh, by the way, feel free to interrupt me if you need to. If you see any things that you want to deal into,
Are there any questions?
Questions? Sure.
We're talking about the farmers and the workers.
Yes.
I assume that, I just want to clarify this. When you send a query to a farmer, farmer just puts it out to the channel to all of the workers that are listening to that channel?
Correct. Every worker listening to that one channel. That channel could be a piece of the key space for that particular key.
Okay, and is there a redundancy with the workers as well?
Absolutely. When you load Roxie and you configure it, you tell Roxie, I want to have this redundancy. By default, it's 2x. Essentially, you will have these pieces of data, these slices, and there will be two nodes that will be loading the same exact slice, and they will be listening to the same channels. You could have 3x, or 4x, or 5x, or whatever you want to do. And you can define that at config time, when you load your data, obviously you will use more space. All those workers, the ones that are listening to the same channel, will be available to respond. If you have only 1 or 2 queries per second, well, maybe all of them will essentially call and say, hey, I have it. When they start being busy, they won't even be responding. Some of them will be busy answering other queries. So at the end, the system balances itself. This is a little bit of the speculative execution that I was talking about. This is, speculative execution essentially on the
Because I know, for example, in Hadoop, the default is one name node, and that's their major point failure.
Yeah, in this case, Roxie doesn't have there is no arbitration service, and there is not a need for it. Yes, you have a farmer that essentially knows where it's like this, but you have as many farmers as nodes. So your load, as long as you have a load balancer that can round robin across the nodes, any farmer will take it, and the workers will automatically know which pieces they have. Yeah, that is true. In Hadoop, the single point of failure problem is kind of difficult. And there are workarounds there where they can do some clustering services to have two named nodes share the same store, but it becomes complex. Roxie delivery engine. I said before, low latency, not key value, and I think I need to put some emphasis there, and this is across SQL in general. In ECL, you define your data layouts. The data model is open. You don't have any limitations. You are not required to specify keys and values for the sake of the process itself. Of course, if you are sorting, you will need to say, well, I want this column or this field to be my key if I have a relational model. And by the way, you can use other models. We normally use relational models, and we will extract unstructured data when we tokenize, for example, our text, and we put it in a relational type model to use it. But you could use ontological models. You could use essentially any data model that you feel comfortable with. You just define your data layout, and that is what you follow across the entire process. So if you have a data set, if your data set has some fields, well, you specify this data set has these fields, and then you define which one, if you need a key for some operation, like sorting or distributing your data, you will say, well, this is the key for this, essentially as a parameter for the operation. But your data layout can be the same along the entire process. It's a lot more streamlined than trying to have in the Hadoop world. I mean, it's not just Hadoop, it is essentially MapReduce. You need to specify a key and a value for every piece of the process. When you need to tell your mappers what they need to do, you need to tell them, well, you need to go look for this data, map this data across the nodes, these are my keys, and build these values. Count me the words, whatever it is. If you need to tell your shuffle process how to shuffle the data, you need to define a key for the shuffle, and the rest is the value of it. And when you have reducers, you simply tell them, well, this is my key now, and this is my value. And these keys and values change over the process. Of course, there is no way they can be the same, which means that if you're not the one who wrote that program, it can become very confusing. So you are not very familiar with data and what the process was trying to do. Roxie is also, I said, high available, scalable. It has a linear scalability, essentially you add more nodes. And if you add more nodes, you have more performance, obviously. Either because you make your slices smaller, and you distribute them across more nodes, and now you have a lot more computing and a lot more relative I/O to the drives. Or you can build redundancy and just tell Roxie, well, instead of having 2x redundancy, do 3x or 4x redundancy. That will increase the number of concurrent queries that you can have at any given time. Then ECL side, and it has a single tool set across the entire process. Sorry. I can show you later. We have a couple, you will probably ask, well, how do I code ECL, right? Yeah, you can use Notepad and code ECL, but that might not be the most efficient way of doing it. We have a couple alternatives there as a integrated development environment. Remember, these guys all came from Borland, and Borland was good at IDs. So the first thing we have is something that we call ECL ID. Essentially, it's an integrated development environment for ECL, with all the nice color coding and contextual help and all the stuff you need, and the integration with the execution and all that. And also, over the last year or so, we developed a plugin for Eclipse. So if you are familiar with Eclipse, well, there you go. Just get the plugin, and it runs like a champ. I'm using it here. So, essentially what I said before. Field computing, lots of nodes, a data-centric language, ECL, and an integrated delivery system. This is a funny one. When we built this slide, I don't remember who built it, but whoever did it, the person put a piece of JavaScript here. So when we look at it, oh, what is this? It was JavaScript, not ECL. So we changed it. Okay, there you go. ECL. How does ECL look? It looks like this. I said it's declarative. Of course, there is flow, yeah, because we have different instructions and then they go along a certain flow. But there is no this crazy flow. Powerful optimizer we developed it over the last 12 years or so. And it feels, since it knows what you are trying to do, what you want to accomplish rather than how to do it, it will define the best way to accomplish it. And it has some of these features. Now you're going to look at me weird. Some of these good features from functional programming languages, like for example, lazy evaluation. So let's say that, for example, you have a piece of code in ECL, and the output that you're expecting is unrelated to that piece of execution. So if you are not producing output, if you're not even writing a file to the file system, I know, yeah, we do have some side effects. We try to avoid them. We need to write something sometimes. So if there is no file that you write to the file system, or output that you put in the screen for that piece of code is not even evaluated. There's no point to it. And this is quite cool. Also, for example, let's say that you want to do a distribute by a key, and you distribute your data across all the nodes by a certain key. That's fine. And now the next operation is a sort by the same key. So the system will say, you should distribute the data across the nodes. Doing a global sort is wasteful because the data is already sorted, well, distributed across the node. You do a local sort on each node, and that's it. Well, the system will change your global sort by a local sort. No point to a global sort if you're already doing the data. So some of these optimizations are good. They provide for very efficient execution plans, and you will see some of those later. The other thing I haven't said before, and it's I think also quite important, the entire platform is coded in C++. So it runs native on the bare operating system, essentially Linux. We do have versions that runs on Windows. We never released it. I don't think we released it. You can combine the Windows if you want. The open source code is there. We used to run it on Windows many years ago. And I think it still compiles and runs. It's just a lot of work to package it in a way that can be presented to the world. And I can tell you, when we started the project to open source it, we need to go through over 1 million lines of code to take care of those nasty comments and other bad things that are in the code. Oh, that took a long process. That was months and months of people looking at code. Open sourcing is hell. Anyway, so when you submit an ECL workflow, that ECL program gets compiled into C++ and into machine code, and is distributed across all the nodes. So even ECL code runs natively on the nodes. There is no abstraction layer in between. There is no virtual machine. There is nothing else. There is no garbage collection. So, well, ECL has. It's declarative. So, well, that gets all hidden. The other cool thing about ECL is that the model that it has makes parallelism in the platform completely abstracted from the developer. You can code the program in ECL, and the program will run in one node, or in your virtual machine if you have one, and you will have 100 nodes. Just throw your data there, and the exact same program will run in 100 nodes. There is no change needed. There is no need to specify the architecture of the system. The system will run in the same exact way. That is also very cool.
you develop your own C++ compiler, or you use whatever's available?
No, good question. That really would be hard. So we use GCC. We have our own our compiler guys. They compile ECL to C++, and then we use GCC. I don't remember which version we use right now, but it doesn't matter. We try to stay current on GCC and try to use the best optimization we can for the hardware. But no, we haven't built our own compiler. That would be a feat on its own. Just GCC itself has a large team of developers, and they are constantly developing just GCC, and it's hard. Well, a few of the things that I said before, so no need to. Here you have some idea of how it looks like. Essentially, you have these attributes, and when you call ECL, this is declarative. So in a way that is declarative programming languages are, in some ways, well, they are not imperative, same as functional programming. So if some of you are familiar with Lisp or Haskell or Clojure or some of these languages, you might know a little bit about this. Essentially, in this case, when you define, when you use this equality sign, you mean essentially is defined as. It's not, there are no variables per se. These are just definitions. So you say, well, this is my definition for this operation, which is a project. I'm going to take data from a data set, and I want to remap it on a different way. I want to move these fields around, or do some transformations, or whatever it is, right? And I apply this transformation on the project, which uses this layout, which is here, and it's not defined here, but anyway. And essentially, when you run your ECL code, all these definitions get essentially in line with the code. Since these values are immutable, and this is another nice thing about ECL, you have very few side effects. So which means that when you are using an attribute, you know that the output will always be the same, it's consistent. There is no global variables that will bite you back when you try to use something. In a traditional non-functional programming model, if you have a function somewhere and you call your function, you don't have any assurance that your function won't reference some global state kept in some variable somewhere there. And well, it's a function that is supposed to add 2 to my number. So I pass 1 and I get 3. I pass 2, I get 4. Well, maybe I pass 5 and I get 1. What's going on? And maybe it is looking for a global variable that says the third time, just return 1. And that can be confusing and lead to errors. Having little side effects, and you need some because again, you need to print the screen and other thing, it's a good thing. Yeah, well, this is you don't have to read the entire thing. Essentially, there is a normal book. All this is from 1991, on Lisp. And the author says something that is quite interesting. And it applies to ECL. I changed Lisp by ECL here, so very simple. So the author says, the book is, if you like functional programming, Lisp particularly, this is a very good book. Essentially what he says is this: in this language, and ECL applies in that case, when you code, you have a need to build an application to ECL, right? Some process that needs to be there, or whatever it is, right, for us. Well, you know what it needs to do. So in a typical programming model, you build it into different functional pieces, and then you start building those pieces. And maybe you need to break them apart into some other pieces, and then build those pieces too. So you go top down, essentially breaking apart your problem into smaller, manageable chunks, and then coding those as you go, until you get down all the way to the language. And the language is down there at the bottom. ECL, and same thing happens with other languages. When you build a program, many times you think, well, I wish my language could do this. I wish ECL had this function. Oh, let me call that function. So you call the function. Now ECL has a new function that will work for you, not only for that program, but for any other alike program. So essentially you are helping your language come up from the bottom and meet you in the middle. It's what is called bottom-up programming. You extend your language to become a sort of domain-specific language to the problem that you normally tackle. Now, you or your team later on, with a similar problem, can reuse that code efficiently. And you know, it doesn't have side effects, so the code is pretty much clean. And if you can, and testing that code is simple as well because of the lack of side effects. So that's I think it's a good feature of this study. Just a couple of things, record definitions. This is a record layout. You have a record that has 3 fields in this case. A first name is a string that can be 50 characters long. A last name, another string, 50 characters long. And an unsigned one, which is an age. And you can now use person rec as an identifier of this record layout. Remember, record layout is defined as person rec. So now person rec can be used across some other pieces of the process. This is a typical way. Essentially, it's not the same way you break your program apart into small pieces. You define all this, you do all these record definitions, and now you can reuse it, or attribute definitions, and you can reuse these attributes across the program as you need. Some functions in CL, just feel free. I haven't mentioned it much, but it is here. Feel free to go to the portal. A ton of documentation there, all the source code for the platform, all the binaries, and all the installation packages for the main Linux distributions. If you have CentOS, Red Hat, Ubuntu, Debian, SUSE, whatever. But just download whatever you want to install. If you have VMs, you can run it in a VM and test it. I have a VM running on my laptop, you'll see it later, with 3 nodes just on the VirtualBox virtual machine. I know quickly on this one. We have a set of machine learning libraries. I'm not going to get into detail there. I have some slides there. Just traditional, well, I don't know how you can say traditional, something that has grown so much over the last 10 years or so, but essentially supervised and unsupervised learning and some statistics, probabilities, correlations, and also some text parts. This is probably quite useful if you don't have the ability to do this today, whatever tool you are using. The ability to do tokenization of text. You have unstructured data, tweets, data coming from emails, whatever it is, and you want to extract, maybe build links across this data, maybe do some analysis, maybe build a recommendation system based on it. Well, there are a lot of functions already built into ECL as part of this machine learning library. As I said before, each one of these functions, which are built in ECL, are part of the language. You just get the module, and you can go reference them directly as if they were built in ECL from the get-go, so as if they were part of ECL. And let's get into Kero now. That's more to the meat. Maybe a year ago, we started thinking, well, this is so cool. People like to learn to play with ECL or whatever. But there are not that many people that want to get into that detail. Many of them prefer to use maybe a graphical environment. What if I could just drag and drop and draw my data workflow and then just run it? I don't care about ECL. I don't care about the platform. I just care about getting my data cleaned or linked or transformed or whatever I need to do. So we started toying with the idea of using Kero Spoon to provide for this graphical type of a front end to a system. And we built some of the functions that we had originally, and we kept adding functions, and we kept adding now machine learning capabilities and others. And you will see which got to a point that is quite complete. Now you can build complete data workflows, and we use it internally as well. We have a system that we use for example, batch processing, which we built in Kero, and we use this integration to do some of these operations. So we have batch operators that are not ECL programs, they are not data analysts, they just know that they are getting this data from the customer, and they need to run these operations on the data, and they just do it. They build their own workflows today using this graphical environment. This is how it looks like. You drag these into your canvas. There are little widgets there, or icons. You link them with little arrows. It's a directed cyclical graph, DAG, for those that are familiar with graph theory, and just essentially express transformation across the system. And it could have different data sets. In this case, and this is a completely unrealistic example, just a toy data set, that it has 4 different data sets, and we are trying to identify essentially universities that have airplanes. And we are taking these 4 data sets, merging this path, which is just a way to say, well, we're going to use these 4 data sets in this process, and then doing a few projects to transform the data to make it look better, or normalize it in some way. And then I do a few joins to find which records match with which records across these data sets, and then just output this. And this is probably a 10 minutes drawing it on the canvas, run it, and it runs. Now, the beauty of this is that without you knowing, it builds ECL in the back end. HPCC provides, in this case Thor, provides for an interface to submit ECL code from a script. It's called ECL Direct. So essentially, you connect to that port, submit your ECL code, and it will run. And it will allow you to do data sprays, so essentially load your data on the cluster, data sprays, essentially unload your data from the cluster, and this takes care of all the distribution of the data. And of course, submit your entire process. So how cool is this? You can build your ECL program without even writing one line of code. Now, if you want to look at your program, the program is available. So once you run this workflow, you can go back and check your program and change it if you want. If you want to learn ECL, this is a great way to learn. JDBC. Sometimes you have some tools that are already built to do standard type of data access, and they use JDBC or ODBC. We don't have ODBC yet. We are working on that. And we have JDBC. So you can use a JDBC interface. You can access your data, you can access your data. Additional JDBC, there are general specifications for how to use it, and it just works. We use it for some of these things as well. For example, for this type of reports. Just standard report. You can use it for Pentaho reports, for example. Or even modules. You can use this to do some of your OLAP MDX slicing and dicing of your data. Build some cubes. Now let's go to the Hadoop comparison. A little bit of what I said before, but adding some more stuff to the discussion. This is what I showed at the beginning. Big data coming on the left-hand side. Thor does the heavy lifting, the cleansing, the profiling of the data, the analytics. Oh, by the way, I didn't mention it before. We have another thing. It's the compiler guys. They can build atomic bombs. So we have, this is cool too. We have a component called salt. Salt is not a component that plugs directly on any of these. Essentially, it's an ECL code generator. It allows you to define with a very small template, essentially 10 or 15 lines of just definitions, template definitions, very simple. Data hygiene, data profiling. And data profiling includes all the histogram computations, identifying every data element across your data sets and the grammar expressions that would match that particular data element and the frequency of the data element or the frequency of related data elements. And also to do this clustering, the fuzzy matching, the linking that I was talking about our person database. Now, the interesting thing about this is how efficient the data scientist or data analyst becomes with this. When we built our original person clustering type of processing, it took us about 10 man years to build it. There was a few thousand lines of ECL, more than a few thousand. And we get some precision of recall, which was around 95% or so, which was very good for data that is dirty and it is not complete and changed and all this stuff. We built SAL. SAL essentially takes this template, generates CL that you can run on your cluster. You can review it, change it, and fix it if you want to improve it, and run it on your cluster. When we built SAL, and we built a template, it took us about, I remember, I think it was like 3 or 4 months to essentially tune the template to what we needed. And we ran it, and we got 99.98% of precision of recall, which is essentially F1, which is a ton of improvement from our 95%. You may say, oh, well, no, it's only 5%. No. If you look at the things that we didn't have properly, with proper precision of recall, which is 5%, and now we have only 0.02% of them, it's a several times improvement, order of magnitude improvement. So it's huge. Now, the interesting thing is that this template itself is about 16 lines of template. It generates about 3,000 lines of ECL code automatically. That ECL code, when it gets submitted, generates about 400,000 lines of C++. Now, imagine that you had a C++ program and try to program that in a reasonable time frame. That will be 100 years. Well, this is what it's shown. Now, let's look at the Hadoop equivalent of this. A little bit more kind of daunting picture. And then I think it's pretty fair, at least on this side, on the Hadoop side, strictly. So you need a few different components. And well, you need to do some workflows. Well, let's use Roxie. And we need also, obviously, we need Hadoop. And how about if I need to do some querying? Well, if I need to do some querying and I need to work for Facebook or not. Well, I want to use Hive. But you know what? Why don't we do some high-level programming for the data workforce there? Well, Hive might not cut it, so let's just big there. Or if you work for Yahoo. And how about the management of the cluster? Oh, this is Chromosphere now. How about security? And you keep adding and each one of the things require an additional component. And the more moving parts you have, the more things that can fail, the more things that will go wrong, the more skills that you need to develop. And it may be a good resume builder, not saying that that's not the case. You're good. But it's difficult. Same thing for data delivery. Data delivery, you have a ton of p-value scores, but if you want to get into more complex analytics, well, you might even start looking at the big values. Well, maybe I need Teradata, maybe I need HANA from SAP. And each one of those have a different weak point. Price, well, all of them. And other than price, HANA. HANA is a great platform for analytics, but it's in memory. So if your data is bigger than memory, well, you're in bad shape. And you probably need some RDBMS system on the front end anyway, because these things may not cut. And of course, the fragmentation here too. We have a ton of different now things to learn and different programming models to plug into the equation. And by the way, even if you use Peak, if you need to do real complex data transformation, data workflows, Peak is not complete by any means. You may need to install to user-defined functions in Java Reduce. So even if you use Peak, you might need to use Java Reduce anyway. Flexible data model, I said this before. You can define how the data model should be for this particular process or across the organization. Well, I'm comfortable with relational models. I'm going to use a relational model. That's fine. That works. Data flow-oriented model. ECL is data flow-oriented. This is a nice way of saying that it's consistent across the execution. Data parallelism is implicit, so you don't care about how many nodes you have, and you don't care about things like, well, what if I have some concurrency that will require locking? No, there's no need for that. ECL takes care of that. All the synchronization primitives are part of ECL, internal to the system. You don't get exposed to them. Do you have control over them? Well, yeah, we have some ways for you to control some of the things. If you really need to control them, you can define well, I don't like how it distributes the data, I want to distribute it a different way. Well, you can do it if you're an expert. But if not, the system will try to make the best choices for you. And it's normally correct. The key there is that we take knowledge that we learn over the years and we move it to the compiler. So essentially the compiler is the best of breed on best practices. Data flows. All the workflows are coded in CI itself. Of course, you can use Pentaho to do the graphical pieces. Well, MapReduce. Some of the things that MapReduce has, I mentioned them before, so I'm not going to get into the details. But one cool thing about ECL is that ECL, when you run ECL, it builds an execution plan. And it looks like this. It's a graphical representation of the workflow as the system understands it. So you told it what needs to be done, the system defines how it is to be doing it, and it will put it in a graphical system. This is an interactive graph. Essentially, it will show you, as the data progresses through the workflow, the number of records that traverse each one of these edges. And even better, it will show you the data skews. It will tell you, well, the heaviest loaded node has 20% more data than my lightest loaded node, which is useful when you're trying to balance your, maybe the system didn't make the best choice, but if you know what happens with the data as it flows, you can very easily abort the workflow and go and implement some other way to distribute data in another way. Optimize the ICD. Well, I thought this was cool, but maybe not. I used it a few times, so now I'm trying to call it. But essentially, it's enterprise grade, not this enterprise, but the real enterprise. Essentially, if you need a production system, a critical operation of the system, and you don't need to get to a ton of additional pieces to try to make this work, this is the system to use. A lot of experience put into that. Many patents, very 40 patents of different components of the system that we released as well, and that the open source models, and very few moving parts. Oh, data types. This is important too. This is a nice thing. When you load data on the system, the spray process, essentially loading data, is record-oriented. It's not block-oriented. Which means that if you have data that is fixed length, or variable length, or XML data, as long as you can provide the record delimiters, the field delimiters for the variable length, or the lengths for the fixed length, or the DOM for your XML data, the system will load the data in a way that records won't get broken apart across different nodes, which is a good way. And also will efficiently use the space in your drives. They won't require fixed blocks of any size. There's no block size in it. And the file system is essentially leveraging the Linux file system, so any Linux file system, anything POSIX compliant. So 73, 64, PTLFS. Yeah, well, that was fun again. I showed oh, and by the way, today we are announcing, we just announced it, the Hadoop integration for it. Essentially, this is a data integration with data stored in HDFS, or data that you want to store in HDFS. If you have a Hadoop system and you want to integrate Roxie, for example, to do data delivery, or you want to integrate Thor to do some other complex process that you don't have a way to do easily on Hadoop, you can use the H2H or Hadoop HDFS data integration for HPCC, whatever it means. So essentially, go here, take a look. We have some good documentation. It's still better. It's not released as final release yet. We want to see if others will find bugs that we haven't found yet. But it seems to work fine. We used it internally for testing, and we even provided to some customers that have this need for integration. This is how we use more. And it's also open source. So you just go there, take it, use it as much as you want, and give us feedback. If it works for you, it's great. If it doesn't work for you, we want to know. We want to fix it. Or, even better, submit patches. We'll use them. Magic Thor. Yeah. And now, I know. Naysayers, they will say, well, I don't have a cluster laying around. I said, well, how about the VM? oh no, that's too hard, I don't have VirtualBox, I need to download VMware, and that's just a little bit. Well, how about using the cloud to test it? Or even to run your process? And you say, oh no, this is too hard, I need to now deploy all these clusters in Amazon, getting there, setting up the images is a nightmare. No, it's not. We have a one-click flow. Essentially, we have a web interface. This is the URL for it. AWS, HPCsystems.com. You can use it. It's free. But the one click is free. What we provide is free. Amazon is not free. You need to pay for those credits. And that's the only thing that you really need to pay. The platform is free. Just go there. It is very easy to set up. Just decide the number of nodes you want to have. It will automatically allocate those nodes. You will allocate the extra, and it will tell you how, so that you know how much you need to pay. The nodes, the extra support nodes that they need, normally a fraction of, well, 2 or 3, depending on the size of the cluster, or 1, right, depending if it's a very small cluster. And it will run them for you. It will start every image, it will start every node, and it will give you all the detailed information on the setup of these nodes, the URLs to connect to for the management, our ECL watch interface, which is the one that allows you to manage the cluster, and every one of the other details that you need to be able to operate this cluster. So it's very easy to use. You can get your data from S3 or any other location in Amazon if you already have it there, and nothing to lose. Simple. This is a comparison, and now I get the criticisms slowly. When I say, yeah, this is a data source. Well, there was a vendor, a hardware vendor. I think I said, yeah, right, he said, Silicon Graphics. They were trying to promote some hardware, this box. I got them from the side. And they said, well, we just broke the data source benchmark. We ran 100 gigabytes of data, which is not 1 terabyte, right? So data source, it was just a fraction. They just used the Hadoop data source code in the Hadoop examples repository, and they ran 100 gigabytes of data. They said they could do that in 130 seconds or so. So I said, you know what, that sounds like a lot of time. Let me try with a small box. So I told one of our guys, hey, you have some time? You want to run this? Just get the Hadoop example, even build the data with Hadoop, and then just use HPC and let's run it and see how it goes. So we ran it. They said that they needed 20 nodes to do this 130 seconds. Well, we had one of these boxes going around. It's a Dell server C6100. It has 4 nodes. 4 nodes. So we run HPC there. We put the 100 gigabytes of data, as this guy did, exact same thing. Run it to HPC and got it to run in 98 seconds. Whatever. Well, and I know if you need to run this pile of servers on this little box, you probably prefer this one, right? But beyond the space and power we need and the cost for the boxes, this is important. This. Look at how many lines of ECL you need to do this process. You really need 1, it's short. Well, you need 2 more. 1 to define your record layout for the input record set, and 1 to define the output, which you don't even need the output. You can just put that in the same line, but well, forget it. Now, go and count, do a WC minus L of the examples directory where just data source and the associated piece of code are, and it's over 700 lines of WS code. So, writing this takes maybe a minute and a half. Writing this takes a long time. And I know, sort, word counts, there are tons of examples there. When you go to more complex things, there are not that many examples. Any. And coding those is hard. Some of the things that I said before, I'm not going to go over this again. So it's just appendix stuff, and then we'll get to the demo. These are some ECL operations and the comparison with SQL. I think this is a little bit useful to know how to do things. Well, if you need to get some data, you just, in ECL, you don't even need to say output. You just give the name of the data set, and that will output everything that is there. If you want to do a filter, well, it's the same as doing a where clause in your SQL with some filtering. Well, in ECL, you just said persons, parentheses, the column or the field equal to whatever, or you can even use partially quality. Like, well, I want to look for every one that has this piece of a string or whatever it is. Same thing for counts, groups, aggregates. So you see that there is an equivalence to SQL for the basic commands. There are a lot of other functions that are ECL that are not part of SQL, or not as easy to build in SQL. That's it. Now, before we get to the Q&A, we have still some time for a little demo,
Sure.
and then we go to the Q&A. Good. So far so good, right? Yeah. Okay, let's do a little demo, real demo. I have here. Let me show you what I have. I have here this guy. This guy is a VM. Okay. This is just a VM. It's a Linux. This is an Ubuntu box. It's running HPCC. Not much to show there. It's just a little VM running 3 nodes. As a matter of fact, it's only one real node. It runs 3 workers in Thor. When you config file, and the configuration for Thor is a graphical configuration, you do it on a web interface. You can define, I want to run more than 1 worker for each node. If I have a ton of I/O, if I have good drives, let's say I have SAS drives, not Sega drives, and I have a ton of memory or whatever, so I want to use more workers than just 1 per node, it might be a good choice. And I use 3 workers because I want to show data SKUs. And with only 1 worker to be shown. Always not a SKU. And I have also this here, which is running you're familiar with Pentaho Kettle Spoon interface. And I show you a few of these workflows. This is one equivalent to the one that I showed before. Essentially, 2 different data sets joining by something and then to resort. And you can see that each one of these little widgets has a little piece of configuration. In this case, this is sort. And you say, well, I want to sort this data set, and I want to do this by this field. Simple. Same thing applies to every one of these. I want to move data to my cluster. Okay, that's fine. I have the data in the landing zone. That's good. What's the file name? What is the logical file name that I want to spread like? And what is the type of records? And we have 2 supported right now, record types in Kettle, essentially fixed length and variable length. We will support XML, but it was a little bit more difficult to show that in a graphical way. So we have to figure out how we're going to do that to allow you to load your DOM and not need to write it from scratch. But anyway, so you define your record layout, your record. In this case, it's a variable. This is each field is separated by a comma. Each record is separated by a carriage return and line feed. And if I have a comma, I quote it with quotes, single quotes, whatever it is. I want to put data on the cluster, and you're familiar with this one because this is a part of. Sorry, came over here. This is part of a Kettle, essentially SSH with the landing zone and putting the data there. And I want to do a join. This is a cool one. I have a couple data sets, a left record set, a right record set, both sides. I want to join by ID on the left record set, an ID on the right record set, and I want to join by using a left outer join. I could have done an inner join, or a right outer join, or whatever I want, right? That's the join type. And I want to put that in a record set named this way. So once you have all this process done, essentially you can just tell it run. And it will create a window that you don't see here. And you can say launch. And it will launch it and give me another little window somewhere. I think my VM is giving me a little bit. There you go. So if you want to validate the ECL code, well, in this case it's in here now. That's good. It's running, you see all the output here, essentially run the entire process. There you go. It's just finished successfully. That's cool. Then we take a look at the results. And by the way, when you do output here, let me show you that. We will do the output of this record set. and you will put it here, see the results. There you go. We got 1, 2, 3, 4, 5 records, and these are the records. Simple. So not much. It's a no-brainer. Essentially, simple to do, simple to connect these little widgets, and it works. Now, the interesting thing is what you have in the backend. If you're familiar with HPCC, you might want to see what it really did. So let's go to this ECL Watch. This interface is essentially the main operational interface to the cluster, where you can say, well, I have these clusters running, I have this configuration, this architecture, and you can see it here. Well, I can see the cluster activity, I can see the queries that I have. In this case, topology of the clusters. I have these clusters. By the way, we are revamping the ECL Watch interface with the more web type interface, which is coming. We have already some prototypes working. And this is the different configuration for the clusters. I didn't mention Thor before. Thor is what I mentioned before on Roxie. Thor is just a special type of Thor which supports for concurrent queries, unlike Thor that is only one query at a time. It's closer to Roxie than Thor. It doesn't have all the high availability of Roxie, of course. Well, anyway, I'm going to go and look at the work units that I just ran. And I have this one here. This is the work unit. Let's take a look. Yeah, sounds like it completed. Well, what can I see from it? Let me see which ECL code got created behind the scenes. Very good. This is my ECL code. Record definitions, see, for the 2 data sets. I'm going to go through detail with this. This is the sort that we have there. We have another record definition there, record layout there. This is transform that is doing as well there, and then the output there, and the join is probably here somewhere in between. Let me see if I can find the join. Yeah, somewhere there. Well, there we go. In any case, yeah, here is the join. There you go. Join. See, this is and I made it on purpose difficult, not a just trivial thing, with a couple more sorts. But what is cool is that, well, I know what I draw in the canvas. I know what the system generated behind the scenes. But what did it execute, really? This ECL code is probably not exactly what it executed. So let's go to the execution plan, which is here in graphs. And let's go to the graph. Very good. This is the graph. Well, not good to see the data execution. It doesn't even show it because it's only like 4 or 3 records. But you can see that it gives you a graphical representation of the execution plan that it actually executed based on that ECL code. It's within these 2 files, it's joining them. Look at this. I never told it to write list. I just told it to sort and create this activity that has as an output the join for those 2 sorted results, right? This sorted data sets. However, the system decided that it would want to write on the drive. Why? Well, this is a very good way to protect your work. What if you had a process that takes 5 days? And what if it had several subgraphs like this one? This one has 2 subgraphs. Well, the system will choose once every while to write a persist file on drive so that if the following process fails, you can always recover back from that one step and not go back all the way to the beginning. You can always tell the system to do it if you want, but if you don't tell it, it will safely take some of its assumptions as well. It takes a little bit more time, but it's far safer. And by the way, we did some comparisons, some benchmarks. We used PicMix, which is a set of benchmarks that Yahoo uses to compare PIC versus Java MapReduce, so that they can see improvement over time. We created a PIC translator to ECL, and we call it Bacon. Bacon is sliced pig, so we thought it was appropriate. Anyway, we do the PicMix benchmarks, the 17 benchmarks, run them through Bacon, and then run the ECL in the exact same cluster. And on average, HPCC was about 4.5 times faster than Hadoop. And this was version 0.23, so it wasn't that old of Hadoop, which is the latest version. Now, Some of these benchmarks ran like, I think the fastest was like 19 times faster in HPCC than Hadoop. Some of them ran about comparable, but HPCC was faster in every one of them. And let me show you a couple more of these workings that are interesting. Like for example, this one here. This is running an naive-based classifier. This is a way to essentially classify based discrete values, and this is building a model. This is just for the kids. This is the graph. It's running a few more records than the other one. See, there you go. So these are the different ages. The number. This shows you how many records run through each one of these edges. Essentially, it gets the read of the file. It does an iterate operation, then a split to run two different sub-processes, essentially two normalizes, and then another split here to run a project, and a join across these two. Say 6 million, 6.9. Essentially, this normalized blows up 494,000 records into 6.9 million records. And then it joins those 6.9 million records with the 404,000 records. I don't know, but we can look at the CL code, but I don't think it's be useful now. But you get an idea of how the graphs look like. I'd like to show you one that has also skills. Hopefully one will run on Thor, not Thor. See? It's barely, you can barely see this. These are monstrous graphs. I aborted some of these. This one. Right? No? I ran a bunch of them in my class. Oh, there you go. This one will work. This one. There you go. This one completed here in 55 seconds. This is the time, by the way. 55.8 seconds. And let's take a look at this one. Let's take a look at the query. Was a relatively simple query. This is building a logistic regression classifier model using a few records as a training set, small training set, just building an inline data set. And let's take a look at the graph. This is a monstrous graph. Look at the graph control. Well, there you go. This is logistic regression. And maybe we can go to, let's take a look at the top. See that you can have a ton of activities. Well, many of the activities happen in parallel. If you have a data set, right now flowing through the graph, you will see that several of these graphs that are at the same place, the same subgraph, will run data across them at the same time. So you have records flowing across all of these, which is not necessarily something that you see when you run a single MapReduce type of process, where you will have essentially every record going through your mapper and then the shuffle and then the reducer. In this case, they parallelize as much as possible across the system, trying to move around this graph. Here's some of the different pieces of it. Some things about the Pentaho, just to finish, I want to make this too long. How my Pentaho window. Oh, this one could be interesting too. This is what I was telling you before. For this logistic regression example, this is the Eclipse, the code we see out in Eclipse. This is the Eclipse plugin. And you can see some of this information directly from here. And you get all the nice coloring, and you have all the execution information here, all your results. These are the results from what we just ran on Pentaho, and some of these are also for the test that I showed. And Pentaho, I may have closed it. Okay, very good. Let's stop it there.
Before we move on to the QA, I just want to first give a great round of applause and thank you and I want to give a special thank you also to Pivotal Labs for this incredibly awesome space. We have form. You can win a Kindle Fire. You can all win the Kindle Fire now. Just fill out the form. If you don't have one, we'll pass up some more. They go into a basket, and one we give away right now. And there's 2 forms there. One is a form to fill out. The other one is one with the URL. You go to that URL, there's a second chance to win a second Kindle Fire. Yes?
We appreciate specific feedback. So if Flavio was great because. If Flavio sucked because. In all honesty, if there are things that you want to learn more about, please tell us. We value this feedback tremendously.
I'll just go recluse myself and cry for a few days, but that's fine.
If anyone needs more forms, I got them here. I see a hand up back there. Can you just pass it straight back? The guy won't. Anybody else need forms? Everyone has?
That's the form?
That guy with the striped shirt also. Oh, that was supposed to go to you though. Yeah, he also had it.
Striped shirt.
I passed you back one, but here's another one. So I'm going to pass the basket around. Whoever hasn't filled out should drop them in or pass the basket on.
Does anyone else need forms? You need forms? No. I pointed out. Any more forms?
If anyone has already filled out their form and wants to throw some QA questions up, that was a quick hand. You get it.
What's the business model? If you're giving out so much stuff for free, where's the catch?
That's a good thing. He's asking, if you're giving all this stuff for free, what's the catch? And you know what? There is no catch. And I tell you why we do it, and you understand. Back in the day, we were doing this, I couldn't even explain my friends what I was doing. Nobody knew about the data, nobody cared. Well, why don't you use Oracle? Right? That was the idea out there. There was nothing out there. It wouldn't make any sense for us to give away what we thought it was our bread and butter, our core technology. Anyone. First of all, nobody would even appreciate it. Second, why would you do that if you're making so much money on data centers? The time changed over the last 6 or so. People started appearing out there, and people started first becoming aware of big data, knowing that there was a value for big data, and having a platform that can do that. Before it was only data, so all spent tons of money. Now they could get it for free. At that point, we thought, and this was it. I was one of the 2 people pushing this. The other one was my boss at the time. Being involved with open source, Linux back in '94 and all that stuff, I thought at this point the only chance we have is to make this platform open source. If we don't, many years down the road, once Hadoop catches up at about the same functionality, we'll end up needing to migrate everything to Hadoop. It wouldn't make any sense to continue developing the platform. Think what happened to Betamax, or Microchannel, or name some of the other great OS2. Oh, I loved OS2. I used to use Warp and OS2 2.1 and 2.0. What happened to them? They were great. Why did they die? Because there was no adoption. You know, we don't want this to happen to this platform. We are passionate about it. So, open source platform, I think it was the best move to gather adoption and to ensure that we have long-term viability. So we're giving it away for free, yes, we continue developing, and we will continue investing on it because we still need to invest on it anyway, because it's going to use internal. But if we have more people using externally, and we go process to go and build new functionality. And this keeps us excited as well. The core developers, I told you, they've been working with us for 12 years, and they've been working together, the same team, for 25 years or so. They need this fresh air, and this is bringing us a ton. So no strings attached. You can go download, everything is there. We have an enterprise license too, which provides support. If you need enterprise support, we'll provide it for you, and we'll charge you for that, obviously. But no other attached. Yeah, that is well, two things. The enterprise license says, no, this is GPL. Don't tell anyone we are looking at potentially moving to Apache. Nothing there yet, so don't take my word. But even GPL, you can use it anywhere you want. But if you don't want to be abiding by the GPL requirements, the ECL code is not forced to do any GPL control application. Essentially, you can build your own ECL code and keep it for you. You don't do anything you want. But if you change the platform, you need to release your source code wherever you sold it. That's the question. It was a little bit of both. So the only difference is the license, enterprise license. Now you get to extend the platform if you want and keep it secret for you. You can sell it and don't tell anyone. We have OEMs as well and other stuff and other agreements. And the support and indemnity for open source. So you don't, if someone tries to sue, if there is another, whatever, another SEO coming and trying to sue people crazy, well, you will be taking that.
We'll take one more question.
Modules that are enterprise modules that you can buy.
We'll take one more question before we do the raffle. Hands?
Now, here's my question for you. Every system has weak points and strong points. You couldn't present your strong points. What are your weak points and what are you planning to do about them in the future?
That's a very good question. We haven't found any weak points yet. Well, it will be too long to answer that. Yes, we know that we have a ton of areas that we like to improve. One of the weak points is we want to improve the community. And we have essentially very few people really active in the community. We have a large number of people now looking at it and using it, but we want to get more people active on it. Getting people enticed to contribute back things like use cases, it's hard. That's the challenge that we have, and we're trying to fix that. Another challenge we have is internal communication. Getting some of these things spread. I come here and talk to you about this. Sometimes we don't even talk about this internally in the company. We have 5,000 employees, and they don't even know what we do. So I try to fix that as well. We have a ton of different challenges in different areas. In the platform itself, we have now new areas that we're exploring. Hybrid computing. We have a couple of great partners. One of them is trying to help us move computing to the memory. Very cool. The other one is trying to help us move some of the computing to FPGA, dedicated hardware within the system, to do some of this edit distance and other performance improvement. But of course, all this takes a lot of work, and we have some limited resources. So anyone that wants to help, welcome.
Okay, now for the raffle collection here, we will select. Okay, you can do it. We're selecting. This is for the winner of a brand new Kindle Fire. One of two that will be given away from tonight's event. What is it?
Doris Emos and Mars Ness.
Yeah, that's what it is. Gorosimos Marnatos? He just left. He just left. Okay. Oh, that's a heck of a loss. He just left. Okay, take another one. Ali Braun.
A-L-E-I-N.
Oh, Lane. Congratulations. Enjoy Kindle Fire. All right, next question. We have... Yes.
Okay, so do you guys have any online developer community to help developers? How active you are?
We have, right now we have a few contributors outside. Some of them contribute in ECL code. Some of them contribute in platform extensions. One of the, I didn't mention this, but one of the contributors is a small company that contributed some additional machine learning capabilities on HPCC. Essentially, they took whatever C++, and that's something that you can also do. And embed C++ into ECL code and build very nice, very clever macros, ECL macros, to provide this transparency. So this became functions of cloud. So there are some areas where we are getting some contributions. There are not that many. And a ton more of the contributions that we are getting are related to, as I said before, bug reports, use cases. We have forums. You can take a look at there. We have also mailing lists in the portal. And whenever we have any other company or individual user trying to contribute something and they have a portal or their website, we try to link to them as well. We have some partners as well in different areas. So it's sorry?
Who staffs the forums? Who staffs the forums?
Who's staffing?
Oh,
Who's the moderator?
forums?
Who's the moderator of the forum?
No, well, it's us. We have a community manager, Trish, and then it is us and other community members responding to the questions. At the beginning, it was mostly us. Now there are a lot of questions that we don't even look at them. There is someone in the community respond to them, so that's cool. Let's work for us, and people get to learn as well.
Questions? Yes.
Are you familiar with FTP?
FTP?
FTP.
Yeah, of course.
Yeah. What's the difference between FTP and ECL or HPCC?
What is FTP?
Yeah.
File transfer protocol?
Yes. Is there a difference between
Yeah, FTP is a network transfer protocol for files.
use FTP?
ECL is a language, a computer language, a declarative language to do data transformation, data queries. It's a completely different area.
I'm curious whether this infrastructure is being used by the LexisNexis products and whether there's any difference between the production code and the community code, and how does the production code flow down to the community level?
Very good question. That is a good question. Well, originally we were thinking of keeping, LexisNexis is essentially our biggest customer, it's HPCC. Well, we are LexisNexis, but we try to keep things separate, rather than create proper interfaces there, people interfaces. So we originally kept 2 different code bases. Oh, that was a bad choice. That's a nightmare to maintain. Now you need to maintain 2 different code bases. Forget it. In version 3.6 we merge both code bases, so essentially everything that LexisNexis uses is simply a community edition. Now, what we don't have published, and we will never probably publish, is the ECL code that we use to do our data processing. As I said before, GPL doesn't force you to abide by it for the ECL code. You get to keep your ECL code, we get to keep ours. The ECL code is our bread and butter of the processes, and we can't release that. That would essentially give our competitors the ability to do exactly what we do. But you have all the patterns. We gave away the grandma's kitchen, but we kept for us the book of recipes. That's essentially what comes in.
Last question of the evening. Yes.
You briefly mentioned use cases, but do you have use cases somewhere? Are they posted?
This is about use cases. We have them posted. We have a ton of these things posted on the portal. So if you go to HPCCsystems.com, you can see some of these use cases. Some of them are internal, and those include things like, for example, linking data records that I mentioned, people data and business data and all that stuff. Doing text analytics. Our legal and news groups, US Legal, is doing a lot of this to link, for example, actors in different cases and all that. We do also analytics on the insurance databases. We manage also insurance databases, claims insurance databases for cars and motor vehicles and house and other stuff. And we do also linking across those. And then we have use cases from other customers. And we have customers we sold some of these systems before it was open source, and we sold some after this was open source. But essentially, we have customers, originally the first customers, the first adopters were intelligence, followed very quickly by intelligence community, federal intelligence, followed very quickly by law enforcement. We deploy some of these systems also in some of the states for some of their data processing, data linking, criminal records and other stuff. We also have some commercial customers, companies that I can't name, unfortunately. They have some of the systems for marketing data, for other data analytics, things like similar to us, scoring and modeling, risk modeling, and risk scoring. A few companies do that as well. What else? I have a probably more, right? Data, scientific data.
So bioinformatics companies
Yep.
are reaching out to us. The problem is standard. I will keep it short, I promise. The problem is standard across all industries, whether it's financial, insurance, healthcare. It's all about variety, volume, and velocity of data. This stuff here is great. If you just Google big data, you'll see tons of articles, you'll see tons of analysts. The problem is the same across all of these industries. That's why you need
Master data management is another area because if you're there, and data warehousing too.
Flavio is dying.
I know.
Dr. Flavio will be here in the front for one-on-one questions afterwards, but we have to wrap it up for now. Thank you all for coming. Thank you, Dr. Flavio Villanustre.